Let's go. 14A. So you've learned discrete random variable. We talked about it being countable. Okay, so data that is countable, that means chapter 14 also is countable. Data that is countable, something that occurs once and then it could either be one or none. Yeah? Now, because it's countable, thanks. Because it's countable, all the theory still stays the same. Expected value is your mean or the average. Your variance, remember I tried to describe it to you, it's the spread of the data because it's measuring from where the mean is, where on average where everyone is sitting at, and then how far away from that mean or the average is. That's what variance represents. Except because it's squared, and I explained why it had to be squared, it's an inflated variable. But it still tells you the spread. That's why you do standard deviation to find the actual units and how far away it is from the data. Okay? Now, when we have binomial, how do you know? There are three conditions there. So, binomial distribution follows what we call a Bernoulli sequence, right here. A Bernoulli sequence describes three components. One, there is only two possible outcomes. So it's one of two outcomes. You either get it or you don't. So the examples are, and they usually call it success, probability of success, and probability of failure, because you only got one or you don't, yeah? So some examples are you either get tails or you don't get tails at all. You either roll a 3 or you don't. Or you can pick a red marble or you don't. Okay, so anything that can be yes and a no. So bi for 2, or like by binary numbers, for example, zeros and ones, the same idea. So if you can only get one option or the other, and it's countable, that's one of the hints they could be binomial problem. Number 2, the probability of success on a single trial is constant. So if you think of back in year 9, year 8, year 10, probability being constant means it's replacement. So if you took out a marble in a bag, let's say there was 10 marbles in a bag, you take out one, there's 9 left. If you do replacement, technically the next draw is still the same. The chances don't change because the number of marbles is still the same. So this one, think of it as probability replacement. So problems where you read it and you can tell that it's a probability with replacement. That's the second thing. So that means all probabilities are going to stay constant. So every time you roll a dice, it's constant because I keep using the same dice. It's the same thing over and over. The chance of getting a 3 is the same. If I pick out something from a bag and I replace it, then every time I draw, it's always going to be the same. The third one is the trials are independent. Now we learned what independent was again. I remind you in chapter 13, where I revised conditional versus independent. But the trials are independent. That means the outcome of one event does not affect another outcome. So flipping a coin, rolling a dice are great examples of independent events. So it has to be independent. All probabilities have to be constant. And there's only 2 possible outcomes. You either get it or you don't. Do you have one of the sheets? Good. Okay, cool. That's the 3 conditions for it to be what we call a Bernoulli sequence. And if it's a Bernoulli sequence, you can use binomial distribution theory. Okay? All right. Let's have a look at an example. Here's rolling a dice. Okay, so I'm rolling a fair 6-sided dice 3 times. I roll it 3 times. Now, again, random variable. I'm going to let capital X be the discrete random variable of getting the number 3. So it's countable. How many times do I get a 3? Do I get it once, twice, 3 times, 4 times? So it's countable. So my data is if I roll it 3 times, 1, 2, and 3, there's a possibility of getting no 3s. So it means I don't get a 3, I don't get a 3, I don't get a 3. Notice I put a dash for complement. That's what complement means not getting what I want. So not getting 3, not getting 3, not getting a 3. That's how I get zeros. Or maybe I could have got not getting a 3, but I get 1 3, and then I don't get a 3. Okay, so that's another combination where I can have X being the number of 3s I get in the 3 rolls. I can get 1. Or I can get 2 3s. So that means that it could look something like getting a 3, getting a 3, getting a 3, then not a 3. Okay, so that would be getting 2 3s. And then obviously getting 3 3s would be all 3 3s, right? The problem here is that even though I wrote before getting 1 3 or getting 2 3s, so getting, say, 2 3s, the problem is there's many different ways I can get it. I didn't have to get a 3 on the first go, and then not a 3 on the second, and then 3 on the third. I could have also got not 3 on the first go, but 3 on the second, 3 on the third. Question is, how many different ways can I get there? This is where the binomial distribution formula comes in, but we're going to look at it on a logical sense. Imagine you didn't know anything about binomial distribution, which my year 8s don't, and I can give them this problem and they'd still be able to solve it. Right? So you can still use what you've learned previously from year 7 to year 11, and you can draw tree diagrams and picture it. We're just giving you a shortcut method. That's what binomial distribution is. Yeah. So in the interest of not knowing any skills that you currently will learn, we are going to do it the long way. So here we go. You can either get a 3 or not a 3. Okay, well, in this case, I use n. So we use the letter n just to keep the tables all the same. So you get a 3 or you don't get a 3. That's your first go. By the time you do the second go, you could get again a 3, or you might not get a 3. Or you might not have got the 3 the first time, but you get a 3 on the second, or you might not get a 3 again. By the third time, you roll the dice. This is all your possibilities. You get a 3, not a 3, 3, not a 3, 3, not a 3, 3, not a 3. So this is what my year 8s would have done as part of one of their tests, where they had to draw out a tree diagram, and then I'd say, what's the sample space? Right, so sample space, here we go. You could have got 3, 3, 3, so all 3s in one go. You could have got 2 3s and then not a 3. You could have got 3, not a 3, then a 3. You could have got a 3, not a 3, not a 3. Then you could have started with an n, so not a 3, 3, 3, not a 3, 3, n, n, 3, and then finally n, n, n. So there's a total of 8 possibilities that you can get there. So answering our distribution question, just putting our probability distribution table, we can say that our possibilities were 0, 1, 2s, and 3s. Well, getting 0 3s was this one. That's not getting a 3 at all, so that represents this one. So how did I get 125 over 216? That was literally doing chances of not getting a 3, chance of not getting a 3, times by chance of not getting a 3. Now let's work out the probabilities. If it's a fair sided dice, what's the chance of getting a 3? 1 6. So that means chance of not getting a 3 must be 5 on 6. But then because I'm rolling the second dice, it's the same thing. The dice hasn't changed. It's still a fair dice, still 6 options. So I still get 1 6, 5 6, 1 6, 5 6, 1 6, 5 6, 1 6, 5 6, 1 6, 5 6, 1 6, 5 6. You see the elements of a Bernoulli sequence? 2 outcomes only. You either get it or you don't. So that's condition 1. Condition 2 is that all probabilities are constant. In this case, yes, they are. And then are they independent? Now you can test it by finding intersections and then finding the probability of A times B times C. And it will be independent as well. So rolling a dice is independent. But those 3 there are the conditions for a Bernoulli sequence. So when we see something like this, this is when we can apply the formula that I'll teach you afterwards. But I want you to see how they arrive at the formula. Okay, so let's think about it. To get 125 over 216, I would have had to do 1 6. Sorry, let me go back. That was when x is equal to 0, so no 3s at all. And that would have been 1 6 times 1 6, oh not 1 6, 5 6 times 5 6 times 5 6, which can be summarized as 5 over 6 cubed. But hopefully you will see a pattern as I've already filled out most of the calculations for you here. Here's your x0. Let's have a look at x1 and see if you can pick out the pattern. Here's x1. This is when you have 1 3s. So 1 3s are, where's the 1 3s? Here's 1 3. Here's 1 3. Here's 1 3. I think that was it. Yeah, that's all there is. So there are 3 1 3s. Just here. I'm obviously missing this extra one here too. So this one is when it's x equals 1. Now I want you to see a pattern when I find the probability. So to get 1 3, that means you need let me do the thing again. 1, 3, no threes, no threes. Yeah, to get 1, 3, the chances are 1, 6, so that's my 1, 6. So I had to have one of them. Then my chances of not getting what I want, I needed 2 of them. Yeah, because out of 3, 1 is what I want, 2 is what I don't want. But look at the pattern. If I asked you to find this one now, n, then 3, then n. N, then 3, then n is this one. So if you follow that branch, can you see you end up with 5, 6, 1, 6, 5, 6. So even if you write it out again, isn't it still interesting? It's still 5, 6 times 1, 6 times 5, 6, which is still the same thing as saying 1, 6, 5 and 6 squared. There's a repetition. These two are still the same. They're just in different order. Yeah, so this order here, this is 1, 6 times 5, 6 squared. This is still 1, 6 times 5, 6 squared. The only difference was the ordering, whether I did 1, 6, then 5, 6, 5, 6, or I did 5, 6, 1, 6, 1, 5, 6. So by the time you go to this next one, n and 3, it's the same thing. The order is different. You still get 5, 6, 5, 6, then 1, 6. But at the end of the day, it's still 1, 6 times 5, 6 squared. So there's a pattern here that you start to recognize or start to see. If I asked you what x equals 2 is, up here, I already filled it out for you. For 2, you need the probability of success. You need 2 of them. You need 2 of what you want, but that means out of 3, there's 1 left that you don't want. Here's what you don't want. That means when I say x equals 2 here, the result doesn't matter about the order. The answer is still going to be 1, 6 squared by 5, 6. That's one of the patterns that you see. So here's the thing. Can you see now, as I color it in green now, when it's x equals 2, let's look at their powers. See, that's 2. The probability of success that you wanted. So what you were looking for is you want 3s. How many 3s did I want? I want 2. I ended up with 2 for the power of 1, 6. So 1, 6 to the power of 2. When I have 1, when x is 1, so that what I want is only one of them, notice that it's only 1, 6 to the power of 1. When I wanted no x's and no 3s, notice that I don't even have a 1, 6. 1, 6 not even there, so technically it's like saying 1, 6 to the power of 0. So this is a pattern that we can see. That means whatever the x is, whatever that little x is, it's the probability of success to the power of how many of those you want. Because this one, that's all I was doing. So 0, you told me the chance of getting a 3 was 1, 6. I need 0 of them. Here, I want 3s, chances were 1, 6 to get a 3, but I only want one of them, so it's to the power of 1. When I say I wanted x equals 2, then chance of getting a 3 is still 1, 6, but I get 2 of them. So really, I've just modeled it here. I said, well, depending on how many x's you want, it's chance of success to the power of x. Then if you model it to get the second one now, how do you model it? Notice here, when we said, how did you get 5, 6? 5, 6 was the complement of getting what you want. So P is the success chances of getting what you want. How do you find the chances of not getting what you want? That will be the total minus what you want. That's why the formula ends up being like this. 1 minus P. Because if it was 30% chance of getting P, then this one must be 70. If this is 60%, that must be 40. Right? So they're always complementing each other. What about the power? Can everyone figure out what the power should be? Yeah, all close. Close. So think about it. I had to know it was 3 trials before. I had to roll it 3 times. So if there was 1 here, that ends up being 2. If this was 0, then that had to be 3. So how would I say? So if I know that I've done, how many rolls did I do? Let's say I did n rolls. If I did n rolls for this dice, and that's how many I want. So how many of these don't I want? How would you work that out? n minus x. So here, this should tell me chances of failure, so chance of not getting what I want n rolls, take away how many ever I want. So if there were 10 rolls and I wanted 7 of them, then this one would be 10 minus 7 gives me 3 that I don't want. So 7 I want, 3 I don't want. So this is the probability of what I want, probability of what I don't want. Number of part of the outcomes that I want, and the number of the failures that I don't want. Last part of the formula that we're missing. There is one little bit that's missing here. Notice here, when I highlight it in blue, x equals 1, x equals 1, x equals 1, there are many different ways that I can write 3n to get 1, 3 in 3 spots. There were many different ways I can write it. Well, in this case, it was it could have been n3n, or it could have been nn3. Yeah, 3 ways. This goes back to combinatorics from last year, if you did it. And if you didn't do it, it might have been in year 10 or something. But combinatorics, this is how many choices do you have? You got 3 options, 1, 2, 3, so n equals 3, and you're choosing how many you actually want. So in this case, I only wanted 1, 3. So out of 3, I'm choosing 1. So the question is, how many can I choose? So if you remember with combinations, I'm looking at how many different ways I can actually move the 1. This is asking 3 choose 1. If you type that on your calculator for your CAS, which my CAS is not working today, you type on your CAS NCR. If you've seen NCR, remember it's NCR on your CAS. Or if you think about it, 3, 1 is like saying 3 choose 1. Okay, so if you think about it logically, you don't even need to use a formula for this one. If you think about it, if you've got 3 options, say 3 texters. Yeah, I had to choose 1. How many different ways can I choose 1? Here's one way. 1, 2, 3. So 3 choose 1, the answer has to be 3 in a logical sense, which makes sense. I ended up with 3 options. Yeah, so 3 potential numbers, and I'm choosing 1. But for those who don't know, the formula is, anyone remember? Did you guys do combinatorics last week? All right, go.
I don't remember it.
All right, well, for those who don't remember, I did give you a formula over here. Just over here for you. So NX, did I write it down for you guys?
Yeah. You remember?
I didn't write it down.
Yeah, you did. So.
I did. I didn't see it. Nah, I didn't give you guys the actual formula. All right, we'll just write it down. It's n factorial over, well, they call it r, but we'll just call it x for now. But it's n minus x factorial. Maybe, yeah. So when you do, yeah. I think they normally use n and r, but same idea. Okay, so that's your general hand formula to calculate that. So in our case, it would have been 3 factorial over 1 factorial times 3 minus 1 factorial. So it ends up being 3 factorial over 1 times 2 factorial. And we know that 3 factorial just means 3 times 2 times 1. And on the bottom, that's 2 times 1. That's why these cancel out and you end up with 3. Okay, so if you like, you can copy that formula down. I thought I would have put it in my notes, actually. And I'll make sure to update the notes. But that's your formula for combinations. Yep. They could, not permutations. Combinations is just that one. They will get you in exam 1 potentially to do that by hand. Yes. So just knowing how to do that. So the last bit of your formula is just this bit here. Nx. So in total, the probability of capital X is equal to little x. Will equal to what you want, chance of what you want, how many of them do you want, chance of what you don't want, and how many of them don't you want, how many different ways can you rearrange that. Okay, so this will tell you the number of different ways that you can rearrange that. And that's your pretty much what we call binomial distribution formula to find the probability of each outcome. Okay? So that formula there, I can show you on the CAS, but my CAS today, I've restarted my computer already, but it's not. This bit here should be probability. That should be distributions. And that one should be binomial PDF. Just under it, if you go to the little menu, if you go down a bit, there's a binomial CDF, which you need to know the difference between the two. PDF is just for the instance. So like what we were doing just then, if you just want to know at x equals 1, what's the chance? So say here you would actually do binom PDF, and then you just got to put in number of trials and the probability of success. Okay, binomial, and then it also tells you how many, what your x value is, so what you want. So you can see when you do it in your CAS, because my CAS is not coming up, but it's a good thing I did some screenshots for it. When it comes up, number of trials, so in our case we roll the dice 3 times. Success, 1 6 to get a 3. X value is what are you looking for? So which instance? Do you want 1 3, 0 3s, 2 3s, or 3 3s? That's where you put it in. So that's a quicker way. So if you put in 3 there, you should get the answer. So that's the order. It's number of trials, probability of success, and then how many of those success do you want? So you can try it for PR of x equals 1. I'm just going to see my calculator open. Is to calculate for one instance. So instead of doing what we did before, see how long that took a long time to do? Instead of doing x equals 1 plus x equals 1 plus x equals 1 to get the answer for 75 on 216, you could do binom PDF. So it would have been 3 trials. Probability of success is 1 6. And how many of these success I want? I want x equals 1. Then it should have gave me 75 on 216 as your answer. Okay. So what is then the difference between PDF and CDF? This is CDF. Let's say I asked you to calculate what's the chances of x being greater than or equal to 1? Meaning, what if I wanted more than just 1 3? So I wanted 1 3 scenario, and then I wanted a 2 3 scenario, and then I want a 3 3 scenario. What's the probability of getting all that? Now, normally you could do probability of x equals 1 plus probability of x equals 2 plus probability of x equals 3. That means you do 3 binom PDF, which takes a long time. So here you would have done binom PDF n, which is 3, probability of success is 1 6, and then 3 plus binom PDF 3, 1 6, and then 2, and then etc. Right? The easier way is to use binom CDF. CDF gives you an interval. Okay, so in this case, it'll be very similar. You can actually type in binom CDF, which is just under the PDF. So I think it's menu 55B rather than A. And it's the same thing again. It's N, P, what is your smaller value to your upper value. So lower value. Okay, so in our case, it would have been 1 to 3. So you can do 1 to 3 in our case, because we got n equals 3. So that would have calculated 1, 2, 3 for you, instead of doing 3 different ones. So that's the difference between CDF and PDF. CDF is cumulative, so it's adding them all in between. And PDF is for one instance. Okay. Did I do an example? Oh, I did. Here we go. Look how organized I was. I had pictures for it already. So if you did forget it, you can follow the pictures there. So you can see lower bound, upper bound. So 3, 1, 6, 1, 3. And this is what it looks like. So instead of doing 75 or 216, 115, and then 1 and 16, takes too long, you get the same answer doing CDF. I probably didn't put it in... Oh, really? Oh. Yeah, I don't know then. What about this one? But if you type there's a fraction, it should come up as a fraction, yeah? Okay, so it must have been If you want to get an actual fraction, you'll probably have to do it through fraction form then. It's a pain. Yeah. But most questions in your exams, they would actually want correct to 4 decimal places. If they're asking for exact value, it's likely it's exam 1. You had to do it by hand. It would have been doable anyway. So they wouldn't make you do something like this in exam 1. Usually it's smaller. Usually like half, 1/8, 3/8, those kind of numbers. All right. All right, team. Let's have a go with the second example. Do we have time? Yeah, we've got a bit of time. Let's just do this one example then. And then I'll leave the rest for you guys to try. But here we go. Textbook question, exercise 14A, question 20. There's a multiple choice test. It has 8 questions. So you have 8 questions, each with 5 possible answers. 5 possible answers. So each one's like A, B, C, D, A, B, C, D, E, A, B, C, D, E, and only one of them is correct. Find the probability that a student who guesses the answer to every question will have no correct answers, 6 or more correct answers, every question correct, given they have 6 or more correct answers. Now, before you start answering this type of problem, you got to try to model it to become a binomial, because currently it's not a binomial. So to make it a binomial, there's a couple things you have to do. Check again, Bernoulli sequence. You need 2 outcomes. So your x variable should be what? So what would I say? Based on the questioning, should hint to you what you want. Let random variable x be. Yeah, so number of correct answers. So number of correct answers. What's the probability of success? 1 in 5. Why is it 1 in 5 and not 1 in 8? Beautiful. There's only A, B, C, D, E options per question. Each question is a trial. See, that tells you how many trials you're doing. So how many questions you're guessing. So in this case, you got 1 in 5 chance to get a correct answer. Beautiful. So that means number of trials. How many trials do you have? 8. There are 8 questions in total that you're doing this repetitively. And because each question still has 5 choices, the probability is constant. That's condition number 2 of your Bernoulli sequence. Now you've modeled it. You either get it correct or you don't. You have same probability for every question you do. So every trial is the same. And it's independent. Whether you get the first question right doesn't mean that the next question you're going to get right. It's all independent of each other. So 3 parts to the Bernoulli sequence. Now we can say, yes, this is binomial. X can be distributed. This is a shorthand method if you didn't know. X can be distributed binomially. So BI, and then you write NP, whatever NP is. So that way you can tell the examiners, instead of saying I'm using binomial distribution, you can do X distributed binomially, and then you write whatever NP is. So in this case, it would be distributed binomially. N is 8. Probability of success is 1/5. Okay? So now the examiners know that you're doing a binomial distribution, hence you're using formulas that are to do with binomial. Let's answer the question. A. Part A. Question A was no correct answers. So that's another way of saying probability of your random variable x to equal 0. Beautiful. So you want no successes. Based on what we've understood so far, if it's binomial, you don't have to draw a tree diagram anymore. You know, out of 8, I want no successes. Chance of success is 1/5, and I want 0 of them. Chance of failure is 4/5. Since 1 is 1/5 to get what you want, then 4/5 is what you don't get. Then how many of those don't you want? Oh, sorry, how many of those do you want? 8. Well, think about it using the formulas 8 minus 0. So you want 8 of those that are all wrong. All 8 questions, you want them all wrong. So this represents correct. This is not correct. So you want all 8 wrong if you're going to get 0 correct, right? Typing in a calculator, that's really just binom, PDF, n, which is 8, probability of success is 1/5, and x is 0. Again, I don't have my CAS at the moment, so you're going to have to do this yourself, or you can do it manually. I mean, you can do it manually as well. 8 choose 0, 1/5 to power 0. Well, maybe that bit you can't. Technically, you can do the 0 bits by hand. Out of curiosity, anyone know what 8 choose none is? Think about it logically. Imagine I had 8 of these markers. How many different ways can I choose none? 1. There's only one way not to choose anything. Yeah. So 8 choose 0 would be 1, and then 1/5 choose 0 is 1 as well. Yeah. And then you just got to work out what 4/5 to the power of 8 is. That should give you the answer. But that would be something you need to know for the exam. They do like to do N0, N1, and NN. I think those are the common ones they usually do. Okay. All right, team. Anyone got the answer? 0.16777? 216. Is that what everyone else got? Yeah, I'm just trusting on whatever you're typing in at the moment. Here we go. B. 6 or more correct answers. So probability of X is greater than or equal to 6. How do we do this? CDF. What's the lower bound and upper bound?
Lower bound 6, upper bound 8.
Beautiful. So in this case, it's probability of 6 plus probability of 7 plus probability of 8. So that would have been X equals 6 plus probability of X equals 7 plus probability of X equals 8. But if you do PDF, that's 3 times you have to do it. Instead, you can just use binom CDF. Same thing again. N is 8. Probability of success is 1/5. Lower bound is 6. And upper bound is 8. Again, I don't know what the answer is for that one. Last one for today so that you can have half an hour to yourself. C. Every question correct. So you want every question to be correct, given that they have 6 or more correct answers. So this is saying I want the probability of every question correct means X equals 8, given that X is already greater than or equal to 6. That's what it's asking. Now remember conditional probability. This is the same as finding probability of intersection of 8 and probability, how do you do it again? Probability of A intersection B. So intersection of 8 and greater than or equal to 6 divided by what's given. So it's probability of X greater than or equal to 6, which we would have calculated from the previous question. Okay. How do you find the top though? This is a typical exam 1 question. How do you find the top? What's probability of X equals 8 intersect X greater than or equal to 6? Think about the language. I want all correct, given, intersecting with X is greater than or equal to 6. Where do they intersect? Because intersection means common, yeah? So what's in common of it equaling to 8 and I need 6 or more? Yeah, it's just 8. Yeah, think about it. If I draw out the line, number line, here's 8, that's X equals 8. The other one is 6 or more. So it's from here, 7, 8. True? So if I said, what's the intersection between the two? It's what's common. They only have this in common. Yeah, so hence, rewriting this line is the same thing as saying probability of X equals 8 divided by probability of X greater than or equal to 6, which you would have found from previous questions. So the only thing you need to work out now is what's the chance of getting all 8 correct, which you can do on PDF. So here you do binom PDF, 8, 1/5, 8, whilst the bottom you would have got from the previous question, which is binom CDF, 8, 1/5, 6 to 8. There you go. Whatever that is, that should be your answer. But that's a good practice so you can see how we use binomial distribution formula to help you do the calculations quicker than doing a tree diagram the traditional way. That only works if probabilities are all constant, all trials are independent, and there are only two possible outcomes. Okay, so it has to follow a Bernoulli sequence. You have to have two possible outcomes, all probabilities are constant, and every trial is independent. If that is true, then you can get your answer. All right, Tim, I'm going to stop the video there. It's 11:02.